Niels Bohr created a model for an atom. Unfortunately, it only really applies to the hydrogen atom, but I want to show it to you. It is in your reference pages, so you need to have those readily available to you at any time because we will be using these repeatedly throughout the course. Now, Bohr's model shows this center area where you have a very dense area. This is the nucleus. This is where your protons and your neutrons are going to be. Out from the dense area are these energy levels. Okay, so you have n equals 1, that's the first energy level, n equals 2 is the next energy level. Here he shows 6, but there's actually many more infinite in theory. There's an infinite number of energy levels. The idea behind these energy levels is that electrons orbit the nucleus on these energy levels. We know now that electrons actually don't orbit. They don't go in one steady ring around the nucleus. They are in orbitals where they're just likely to be found. But for the purpose of what we're trying to do here, we're going to look at orbits. Niels Bohr said that an electron can jump orbits. It can jump energy levels. So an electron that's at this ground state, at this n equals 1, this first energy level, it can jump to this next energy level if it receives or if it absorbs enough energy to do so. And that amount of energy is actually called a quantum. Okay, the amount of energy that is required for an electron to go from one energy level to the next. So that electron would absorb that much energy. Now the thing is, when that electron that's now excited because it has all of this energy, when that electron releases that energy, it's going to drop back down to its regular state, its ground state is what it's called. So the electron will drop back down to its ground state, but in the process it releases light. It emits light. So that's actually how we see light, is electrons releasing this bit of light because they are releasing this bit of energy. Now, this model here shows how much energy, or not necessarily energy, but the wavelength of light that would be released in each of these scenarios. If an electron went from the second energy level down to the first, it would release a wavelength of 122 nanometers. Okay, so you need to remember that nano is 10 to the negative 9th. So this is 122 times 10 to the negative 9th meters. Okay. If an electron, a very, very excited electron, was over here, this is this n equals 4 orbital or orbit. What if it dropped down to 1? So it dropped down 3 energy levels. It's going to release light, it's going to emit light at a wavelength of 97 nanometers. So again, that's 97 times 10 to the negative 9th meters. You just want to be aware of that nanometers versus meters detail, otherwise your calculations might be wrong. Now, what if the electron went from this n equals 5 state to n equals 3? The light, the wavelength of light that it is releasing is 1,282 nanometers. Okay, so now we have very different numbers, but using these nanometers, we can actually determine some additional things. We can determine the frequency. We can determine the energy that is being released as well. Now, if it was going the other way, you would have to assume that it is the opposite. How much energy is being required for an electron to go from this, what is this one? N equals 3, this third energy level, to the sixth energy level. We'll do problems that look at both of those. Okay. So, in addition to the Bohr model, you also have an electromagnetic spectrum. Each of those wavelengths corresponds to a different type of radiation or a different type of light. Visible light is the light that we can see. These are the colors that we can see. And we can actually determine that our visible light spectrum only goes from 4 times 10 to the negative 7 meters to 7 times 10 to the negative 7 meters. This is a very small range. Just right here is all that we can see. We know that we cannot see ultraviolet rays or X-rays or gamma rays. We can't see infrared rays, not with the naked eye anyway. Can't see microwaves, we can't see radio waves. So these are all different wavelengths that we are not capable of seeing with the naked eye. We are capable of seeing the visible light spectrum. Now, if we have a wavelength of 97 times 10 to the negative 9th meters, okay, or yeah, this is meters because we have converted it from nanometers. We can actually look at what kind of light that is by looking at these top values up here. This is times 10 to the negative 9th, so you're looking at this right here. It's 97 times 10 to the negative 9th, and that's not really in scientific notation, so really we could say that it is 9.7 times 10 to the negative 8th, right? This number got smaller, so this number must get bigger. So times 10 to the negative 8th is going to be somewhere right here. This might be an ultraviolet radiation, or it might be X-ray radiation. Either way, it's going to be in this vicinity. We can then take this value, this wavelength, to determine the frequency of the radiation. And once we have frequency, we can determine the amount of energy that that wavelength and that radiation is carrying. So in the next video, I'll show you the 2 equations that you'll need to use for each of those calculations, and then we'll do some practice problems as well.